Welcome to HEC Montreal's Chair in Energy Sector Management webinar series. I'm Joanne Whitmore, Senior Researcher at the Chair. For those of you who don't know us, we're the first North American chair in a Francophone Business School of Management to address issues related to sustainable management of energy resources. So today's presentation will be looking at the pros and cons of using natural gas in freight transportation as a measure for reaching climate change goals. Our speaker is Rosa Dominguez-Faus. She's a program manager and senior researcher at the Sustainable Transportation Energy Pathways program at the University of California, Davis. She holds a Ph.D. in environmental engineering, and her research has focused on alternative fuels, including biofuels, natural gas, renewable natural gas, and hydrogen. She's published many reports on the subject, including exploring the role of natural gas in U.S. trucking, as well as carbon intensity of natural gas vehicles in Category 8 trucks. So just before we start, I'll just provide a little bit of the context for this webinar. As many of you know, natural gas is often viewed as a transition fuel in the context of climate change, as it's less greenhouse gas intensive at the consumption point than other fossil fuels, notably with coal. This has led many governments and industry officials to consider the use of natural gas as an alternative fuel to diesel in the transportation sector for achieving greenhouse gas reduction. In Quebec, freight transportation, which includes trucks, ships, and planes, account for almost 14% of the province's GHGs, and trucks account for about 79% of that portion. It's the fastest growing source of emission and is expected to surpass emissions from passenger transportation by 2030. In response to this, and faced with ambitious greenhouse gas reduction targets, the Quebec government announced in its 2030 energy policy that it would support the conversion of transportation vehicles to fuels with lower carbon content, in particular liquefied natural gas and compressed natural gas, and that it would promote a large-scale conversion of natural gas to freight transportation and heavy-duty vehicles. However, it's important that policy decisions be based on the most recent scientific data available, as well as be assessed and understood from a broader perspective. And this is why we're doing this webinar, because so far, unfortunately, this hasn't been the case in the public discussion on the topic. So today's presentation should help us understand from a scientific and more objective basis to what extent using natural gas in transportation can help us achieve greenhouse gas reduction, as well as what should be considered when looking at such an approach in the context of climate change mitigation strategy. As some of you know, California was one of the first jurisdictions to introduce large-scale conversion to natural gas for its truck fleets, and also Paris is another example. Their main objective, however, was to reduce smog in their city, hence the net zero programs for natural gas vehicle, which refers to NOx emissions, not greenhouse gases. The success of the program has been great from an air pollution perspective. However, from a climate perspective, researchers at UC Davis found there were some setbacks associated with the use of natural gas in vehicles. So without further ado, it's my pleasure to welcome Rosa. Her presentation will last about 40 minutes. And then we'll have about 20 minutes to take questions. Hopefully, we'll have there's over 70 people that have registered to this webinar. So we'll do our best to answer the question and perhaps even extend 10 minutes if people want. Participants can send in their question at any time during the presentation by typing them into the GoToWebinar window on the right side. You'll see there should be a little window that says questions, so you can send them in and I'll read them, and then Rosa can answer them. So Rosa, the floor is yours, and thank you everyone for being here.
Okay, thank you, Joanne, and thank you HEC Montreal for inviting me. I'm very excited to be here. It's exciting to see that Canada is also, and Quebec in particular, is interested in reducing their greenhouse gas emissions, and they're thinking of natural gas as an option, using natural gas in transportation. Today I will present the results of research at the STEPS group that I lead here in UC Davis, California, and it will be about what we've learned about the pros and cons of natural gas used in transportation. It will be in the California context and the US context. And we can discuss differences with Quebec later, with hopefully with questions and answers. Okay. Okay, so first I will just briefly discuss, talk about STEPS. It's the group that I am managing. It's a multidisciplinary research consortium, part of the Institute of Transportation Studies at the University of California. We like to think we're world-leading university center on transportation. We produce insights, tools, trying to incorporate technical and economic realities and study transportation energy futures in California, the US, and the world. We are a consortium. We bring together the most energy and auto manufacturers, government agencies, and other stakeholders to collaborate on sustainable vehicle and energy solutions and inform industry planning and government policy. If you want more information about STEPS, you can always visit our website. So I will briefly give a context for natural gas use in transportation, although Joan has done a really good job, so I'll go really quick. Both Quebec and California participate in the Western Climate Initiative. Quebec has GHG target reductions in transportation, 20% reductions by 2020, 35.5% reductions by 2030, and 80% reductions by 2050. Freight accounts for 37% of all energy consumed, and it's as is the case in California, it's one of the biggest growing sector in terms of GHG emissions. So it makes sense that we try to target transportation. And one option is to use natural gas for vehicles. And I'm showing I'm going to show some claims that say, hey, natural gas, a problem solution, generally less expensive and always more environmentally friendly than diesel. And this is from Gas Metro sustainability report that 19,000 tons of CO2 equivalent have been avoided by switching to renewable natural gas. Another claim, this case by ENGIE, freight operator. NGVs, natural gas vehicles, reduce CO2 emissions by 25% compared to gasoline, and reduces NOx emissions by 80% compared to light diesel vehicles. So a couple of things here. Are we talking about, what kind of pollutant are we talking about here? Are we talking about criteria emissions or GHG emissions? Because they are different, right? Oftentimes I would say natural gas vehicles are touted as near zero emission vehicles. But that's true, but that refers to criteria pollutant only. That means natural gas is indeed low in NOx and PM, and that's why the denomination of near ZEV, but that refers to criteria pollutants, not GHG. Some claims, including LCFS credits in California, low carbon fuel standard credits, claim that natural gas can produce about 20% reduction from gasoline and diesel. Not 100% reduction, so not a ZEV, but about 20%. And that's what we're going to try to evaluate, how these claims are, how true are these claims. If we look at, when we're looking at the emissions from transportation, we look at what's coming out of the engine, out of the vehicle, so combustion emissions. And yes, natural gas emits less CO2 per energy produced than diesel. But it's a little more complicated than that, right? I mean, that would be only the emissions from the vehicle. And when we're talking about fuel use, we want to see how the big picture looks like. What's the life cycle analysis, or what we call the well-to-wheels carbon intensity. The well-to-wheels is defined by each stage from production of the fuel, refining it, and then putting it in the pump, and then putting it in the vehicle and using it. We can typically divide the whole life cycle or well-to-wheels into the first part, the well-to-pump. That's what we sometimes call the fuel cycle, and that's what it takes to produce and bring the fuel to the station. And then what we call the pump-to-wheels, which is what it is in the use part, in the end use, right? So for now, I'm just going to focus on the upstream. So the well-to-pump, upstream or fuel cycle of methane, of natural gas, requires that we look into an important issue, which is methane leakage. This is a better picture of the natural gas supply chain. So if you see, you have producing wheels, and then gathering lines and processing plants, then big transmission lines that might go to storage, city gate, and then distribution system that goes to the end users. And in here we have an LNG station that skips the distribution. It goes from the LNG, from the transmission line to a liquefying plant, and then it will be transported in liquefier tanks to the LNG station. And then we have a CNG station, which goes from the distribution line to the station as natural gas. And in the station it is compressed and then injected into the vehicle. So there is methane leakage in every stage of this supply chain. So we have during production wells, gathering line, processing plants, compressor stations and transmission. We have them in the distribution system. We have them in the transport to the stations. And then we also have them in the stations and in the vehicle. But that, I'm not talking about that right now. So that's why I'm marking it. I'm talking about the upstream. So I want to show you this video by the EPA that is looking at these methane leaks in the upstream. So you will see this is using infrared cameras, and the quality of the video is not great, but you can see, for example, here in this is marking in the circle the part that's looking in the regular camera, and then with an infrared camera you can see that there are leaks. So that's the way we see how the leaks are happening. We have several examples here. We're looking at the joints, and you pay attention to how this is a measurement. This is how EPA is measuring the leaks. More processing plant leaks. We'll see leaks throughout the supply chain. Just bear with me with a second. Hopefully you see the black fumes that are normally not visible in the naked eye. And that's happening here in the distribution system. You don't see anything here, and now you see it. That's the same thing with the infrared, right? So methane leakage is happening even though we don't see it. Right, another one, manhole that's open, and then you see all the methane leaking. A road, a pipeline, maybe that's the repair, or we've seen that they leak. This is probably a storage tank. I know it's hard to see, but you can see that there are these leaks coming from the little pipes. We'll see that there is leakage in the pipelines, and that's coming next. This is going to be shown using aerial surveys. So basically same technology, but from the air. So this is pipelines that are leaking. A pipeline that's leaking. Oil production well is leaking too. And then more storage. Okay, point is there is leakage, even if we don't know it, even if we don't see it, but we do know it. This is, EPA has been monitoring methane leakage in the natural gas and the oil systems for a while now, and measuring the leakage at each stage. They have kind of come up with this number. It's overall the system leaks about 1.5% of what's produced. So basically about 1.5% of the natural gas that we consume, it's leakage. It's leaking to the atmosphere. We're losing this to the atmosphere, and that's bad because methane is a powerful greenhouse gas. So we know that's not a great idea. And this is more or less how it is distributed. 0.2% it's happening during drilling and fracturing. 0.4% in production and processing, 0.2%, 0.7% in the transportation and distribution system, and the end use, which in our case is transportation, it's not included in the EPA inventory. EPA estimates of leakage go up and down a little depending on the year, and that has to do with new regulations coming in place and people being maybe a little cleaner, but it also has to do with the method, okay? But anyway, if you can see in this table, this is directly out of the greenhouse gas inventory by the EPA. And if we see the first line after the methane, the CH4, this is natural gas systems, and we can see that it's been it's been kind of going down and then up a little bit. It varies a little bit, okay? So I mean, there's a little bit of uncertainty in the actual quantity that's being emitted, but we can deal with it. Now, production of natural gas also changes a little over the years, so we can see gross withdrawals from gas wells also changes a little bit. If you divide what we measure it's being leaked into what it's being produced, that's how we come up with this 1.5% leakage. So just keep this number in mind because that will be the basis for a lot of my calculations. However, many disagree with EPA. And in the US, in the past, I would say 4 years, has been an intense debate about whether EPA has the accurate estimates for methane leakage. There's been at least 16 major studies by different universities and centers, all under the umbrella of the EDF, the Environmental Defense Fund, and their scientists. And they have comprised the entire natural gas system. Some people have looked at fields and natural gas production. Some others have looked at distribution systems. Some others have looked at urban systems. Others have looked at transmission lines. Others at storage, etc. So the entire system has been looked at, and the results been that they found a range of estimates. So who is right? Again, a lot of uncertainty. So one main difference besides the regionality, there's some regions that have found there's some regions where drillers seem to be leaking more than others, and that seems to be related to the fact that some states have better regulations about methane control. It's been shown that some companies are better than others, also maybe due to regulations, company culture. But I think the main difference between the studies is the methodology of how this methane has been estimated. So EPA, if you remember how in the video there was this person with a machine was taking a measurement of a specific device. So now you have an estimate, an emission factor from this device, and then you have an inventory of the amount of devices you have like that. So you multiply your emission factor by the number of devices, and then there is your estimate. That's what we call bottom-up. Now, some independent studies have also done bottom-up, but some have done what we call top-down, which would be they're taking atmospheric samples, right, of the air in general. They're not specifically attributed to any device or activity, but they're just taking measurements in the air. And what we found systematically is that these top-down studies find larger concentrations of methane in the atmosphere that you would expect if you were to believe the bottom-up, you take the values from the bottom-up studies. So why is that? There's a few theories, and there's a few reasons, I would say. One is that it looks like EPA might be missing small numbers of super emitters. In other words, in a bunch of studies, it's been found that there is a few companies that are responsible for the majority of emissions, again reflecting company culture. Or in a transmission system, even belonging to the same company, or a distribution system belonging to the same company, some sites were responsible for the majority of the leaks. So maybe EPA sample of measurements is not looking at the entire population. And that can be explained, and I think that kind of makes sense because there is not, the EPA is measuring this with some of volunteer companies. So some people are volunteering their facilities for EPA to come and take measurements. So I think you can expect that, you know, the best practitioners and the best kind of performers are going to be in the sample, not the bad performers. So that's one reason why we see more methane in the atmosphere than we would expect based on EPA inventory. Another reason is that we're not measuring, we don't know what's going on with abandoned wells. I mean, we don't even know where they are sometimes. We don't have a good record of all the wells that, you know, happened, that were drilled and operating, and maybe they've been closed, and there was not a standard method of closing it. So these are also leaking. So Mary Kang from Princeton published a paper and looking at the contribution of methane to overall methane from abandoned wells in Pennsylvania, and she found that these abandoned wells might be contributing 0.3 to 0.5% percentage point. So meta-analysis of all these studies suggest that the actual leakage might be a little higher than what EPA estimates. So again, EPA's number is 1.5%. If we correct it, it could be something up to between 2 and 3%, not more than 3%. If we add abandoned wells, then it may be up to 3.5%. That's the leakage. For my studies, I would use 1.5 or even lower. So I want to point out that there's been an effort to reduce upstream methane leakage. EPA has this voluntary program where people are participating, and it's called the Natural Gas STAR program. STAR programs also exist for coal mining, from agriculture, from landfills, and this is basically EPA is establishing where the leaks are and try to measuring how much they are, and then it's suggesting a series of measurements, measures that you could take in order to reduce this leakage, you know, new technologies, etc. And what's found is that most of these technologies have a payback period of less than 3 years, sometimes just even a few months. So it's on the economic interest of the companies to try to reduce their leakage by applying these things. So there's a little progress. I have to say this payback period is based on a time where natural gas was more expensive. Now with natural gas being so cheap, the benefits of not wasting natural gas are somewhat reduced. But there's progress. About 16% from 2015 to 2016, about 16% of the leakage was reduced, despite the fact that production increased by 35%. But the amount that we are not emitting with this program is still only a small percentage of what's being emitted. So in summary, what I have explained about upstream leakage is that it's variable, depends on company culture and geography, which often reflect regulations. It depends on how you measure it. The numbers, 1.5%, it could be up to 3%, 3.5%. In some specific cases, some studies have found as high as 8%, but that's been difficult to attribute to sources. So we don't know whether it's coming from a natural gas well, from an oil well, from an abandoned well, so there's uncertainty in there. My way to deal with uncertainty in this case is I'll just test different scenarios for leakage. I'll do the baseline, and that would be at 1.5%. I test zero leakage scenario, and then I can test higher up to 10%, but that's not really interesting. And I will get to that in a minute. But now I want you to see this. This is part of my results. We're not talking about the results right now. What I want you to see, this is the carbon intensity of diesel and 3 different options for natural gas. And what I want you to see is that the gray area, which is what's happening in the vehicle, the emissions that come from the vehicle, is a major part in the overall carbon intensity than what's happening in the upstream. So even though yes, we want to reduce methane leakage, and it's important to reduce methane leakage, and try to be very accurate in our estimates of what's going on in the upstream, I want you to understand that the biggest contribution to carbon emissions happen in the vehicle. So that must not be overlooked. So remember how I was not looking at what happens in the vehicle? So now I'm going to talk about what's happening in the vehicle, right? So no upstream, and we'll look at the pump to wells, although I have to say we don't have a lot of information about the pump. So it will be mostly just about the vehicle. Okay? So there is methane leaking from the natural gas trucks, and that's not happening as much in diesel trucks. So that is a little bit contested or contending, but again, uncertainty in data. I have to say I'm using vehicle data that's provided by Westport. Westport is one of our consortium members, and it's a lovely relationship. I love them. So, and these might need to get updated. Haven't talked to them in a while, but this is what they provided a couple of years ago when I did this study. So one thing is to see that while there is basically no methane leakage in the diesel trucks, there is methane leakage in the natural gas trucks. And it depends on the engine. And there's different type of engines, and then there's different types of applications of this engine. So it's very specific to the application. So just to note that I'm doing long-haul trucks. So these numbers apply to long-haul trucks. Other applications will have another emission profile because they will have different drive cycles, and that affects the emissions. And we're not going to start talking about emissions and drive cycles, but we'll just state that that's the case. Other studies, and I don't know what the claims that we had at the beginning of the presentation are using, but I know the California Resources Board is using the numbers for natural gas, is assuming it's being used in buses and taxis. And while my study will be using it in long-haul trucks. That is important because of the different drive cycles of these applications that affect the emissions and the efficiencies. And it's important because depending on which fuel it's substituting, whether it is gasoline or diesel, then we'll notice that these differences are even more important. So why does it matter that which fuel it substitutes? It's really related to the efficiency of the combustion process. It's not so much the fuel, it's the engine that will be used to combust this fuel. So diesel uses compression ignition engines with an efficiency of 55% average. I'm just talking about an average here. Gasoline and natural gas both use spark ignition engines. In general, spark ignition engines are about 10% less efficient than compression ignition engines. So when you are comparing natural gas to diesel, even though natural gas might be a lower carbon fuel because you're going to have to use a less efficient engine and you're going to have to burn more of the fuel, you might be emitting more carbon in the end. For gasoline, because you are using spark ignition and natural gas is using spark ignition, there is not a fuel economy penalty. So in taxis and buses that use gasoline, no difference in efficiency. in long-haul trucks, 10% efficiency loss when switching to natural gas, and that's going to be very important. Newer models seem to control crankcase leakage, but exhaust CH4 is still a bit tricky. And I'm not going to talk too much about that, but just saying that reducing the methane leakage in the vehicle is going to be important, and I think it's possible to do. It looks like about half of the current leakage in the vehicle can be controlled. The other half is a little difficult, so I don't think it's going to happen that we have zero methane leakage from the vehicle. Westport designs the HPDI dual fuel engine, and that's an engine that uses 90% natural gas, but it starts with diesel. So it can start with compression ignition and therefore maintain the high efficiency levels of a diesel truck. The most common though is the spark ignition efficiency. I will try both in my model, so to see how these differences in efficiency of the truck will impact the results. So now I talked about the methane leakage upstream, I talked the methane leakage in the vehicle, and I'm going to add all this to my model, which is a grid model, and calculate the well-to-wheel carbon intensity. And just a reminder of baseline assumptions, because I'm going to do a baseline scenario and then I'm going to modify scenarios to see the impact of the different variables. This is the results. This is the figure that I show you, but now we're going to pay attention to the results. So left column is diesel, and right three columns are natural gas in the form of CNG used in a spark ignition engine, natural gas in the form of LNG used in a spark ignition engine, and natural gas in the form of LNG used in a compression ignition engine. So what we find is that both, there is not, if we look at the two in the middle, which is same engine but natural gas, different storage, there's not a big difference in the overall kind of emissions, but both produce an increment of carbon emissions with respect to diesel, 6% in the case of CNG and 4% in the case of LNG. Now, if we were to use, so the other thing that we can see here, just like I said, the gray area is what the gray color is what happens in the vehicle. The solid is CO2 emissions. The stripes are methane emissions. So you can see how much in the vehicle is contributed by methane and how much is contributed by CO2. The same in the fuel cycle or the upstream, which is both the yellow, the orange and the blue. The solid again is the CO2 emissions. The stripes is what's contributed by methane leakage. So if you look at the difference between CNG and LNG in terms of methane, we can see that methane has a bigger impact in the CNG pathway than the LNG pathway. And that is because the CNG pathway will use the local distribution system to transport the gas into the stations where it is compressed, whereas the LNG's pathway will just take it from the big transmission lines into a liquefaction facility and then will transport it as LNG and to the refueling station. Now LNG has boil off, and that is included in this calculation. But still, methane leakage affects the CNG pathway more than the LNG pathway. Other studies. So let me get back to this for a second. So natural gas is basically, if used in spark ignition engines, a little bit less efficient than diesel engines, basically increase the carbon intensity of diesel. And only if you move to the compression ignition engines, you have a benefit. And that is, again, because even though natural gas per se as a fuel might be a lower carbon content than diesel, because you have to use more to produce the same work, the same miles, to go the same miles, then you have to, in the end you emit that. That's kind of shocking for a lot of people. And I have been discussing this with a lot of people in California, because as you know, we have big incentives for natural gas vehicles, and that was not very well received. And good thing for me, I guess, is other studies have found similar estimates. And again, the estimates vary. There's uncertainty. So I will not say that my numbers are perfectly accurate. There's variability, there's uncertainty. So, you know, estimates can move up and down a little bit. But I would say that other studies in the US that have been focusing on long-haul trucks have found that natural gas does indeed increase the emissions by a little bit. That's the case of the Carnegie Mellon University, a really important center for life cycle analysis. Columbia University with the EDF is using a different approach, but basically found that natural gas leads to damage to the climate for several decades, and it's only after 72 years or 90 years for the different kind of storage that you get any benefit. The LCFS, though, says there's reduction, and that is, again, because of the application is different. Buses and taxis are using spark ignition engines as gasoline engines, so there's no fuel penalty there. So, variability and uncertainty. Why are all these different? Which variables are more important? Because in the end, that's, I mean, we can argue forever how much leakage is actually happening in the upstream, how much leakage is actually happening in the vehicle. I have to deal with uncertainty somehow, and my way, the way we do it in LCA and in modeling in general, is we try to test the sensitivities. So I have, in this graph, I show the diesel baseline and then the natural gas baseline. This baseline is using the 1.5% leakage and the vehicle emissions that I explained provided by Westport. So we see, again, CNG produces an increment of 6%, LNG an increment of 4%. Now, I'm just going to test what happens. I don't know what the leakage is and if we can reduce it. I'm just going to hypothesize we can eliminate it completely. So what if there is zero upstream methane leakage? So what we see is that CNG will go to -3, so there will be a 3% reduction from diesel. And in the case of LNG, still an increment. So upstream methane leakage doesn't affect LNG as much as it affects CNG, that jumped from +6 to -3. LNG jumped from +4 to +1. Now, I'm going to put everything back to my baseline parameters, and I'm going to just switch the methane leakage from the vehicle. I said I think it's going to be really hard to completely eliminate methane leakage from the vehicle, but I'm just going to hypothesize it's possible. So if we were to do that, we would jump from 6 to -1 in the case of CNG, not such a big reduction as when reducing the methane leakage in the upstream, but we would find that in the case of LNG, that would be a major contributor from +4 to -4. Finally, I am going to put everything back to my baseline conditions and change the fuel economy. I'm just going to assume that natural gas vehicles are as efficient as diesel vehicles. And what we find is for the case of CNG, that is as effective as reducing the entire upstream methane leakage. And in the case of LNG, it's even more dramatic than, you know, any of the other measures. And it indeed goes from +4 to -6. So there's actual reductions if we do these things. Another kind of sensitivity test that we run is, you know, let's see, there's uncertainty about methane leakage. I'm just going to test from 0 to 10%. This is like too radical. It's not there, but let's see what happens. And this is the dashed line is the diesel baseline. This would be the LNG in the compression ignition. This would be the LNG, the green line is the LNG in the spark ignition, and the orange line is the CNG in the spark ignition engine. So one thing that we see here is that CNG is much more sensitive to methane leakage than LNG. And the other thing that we see here is that for any given storage type, no, let's not mix it, just LNG and LNG, only the compression ignition engine, the one with the high efficiency, is actually below the diesel line at some point. With the spark ignition, leakage has to be basically 0 or under 0. And with the compression ignition, kind of up to 3% to break even. That's to break even, not to produce any benefit. The conclusion is that there is variability besides uncertainty. One value does not fit all. One single estimate is not valid, not only in the upstream but also in the vehicle leakage and fuel economy, which I've noticed there are larger sensitivities to these two parameters that are normally overlooked. A lot of the focus is on the upstream, and that's important, but also what happens in the vehicle is important. I am not saying that natural gas cannot provide GHG reductions. What I am saying is that it is not always the case. Upstream leakage is important, but so is what happens in the vehicle. The vehicle specs will depend on the applications, and the fuel is substitutes. It's not the same whether it is bus or truck or marine, and I know there's interest in marine too, and I think it's actually going to be very beneficial in marine. And there are ways to lower the carbon intensity, reduce the upstream methane leakage, reduce the vehicle leakage, increase the fuel economy. However, using any of these, reductions will be modest. It's definitely not a near ZEF in terms of GHG. Near ZEF applies to other kind of pollutants, not carbon pollutants. There is a possibility of lowering the carbon intensity of natural gas considerably by blending it with hydrogen or renewable natural gas. And we have produced another study on the potential of renewable gas in the state of California. Didn't think I have time to discuss that, but it will, maybe we can discuss in a webinar. Most of the RNG study, as well as the just natural gas, fossil natural gas studies reports are in our website. Here are the links, and with that, I would like to thank you for your attention, and I'm open to questions.
Thank you, Rosa. This was very informative. We have actually quite a few questions. I think if we can give a short answer of 1 to 2 minutes to try to get through as many, that would be great. Okay. So I'll just go through them and then just see what you can answer. So the first question we asked: Are there any meta-analysis done on the life cycle GHG emissions of natural gas, in particular the types of natural gas used in Quebec?
I don't know. Yeah, I don't know. I mean, Canadians have their own life cycle analysis model, the GHG that I have not used. It's based on the LEM model, which was developed by my group many years ago. So is the GRID model, so we share a lot of features. I don't care normally so much about the differences in the model, about as much as the differences in the assumptions, the input parameters, these input variables, which I hope I've argued they are uncertain, and we can argue forever, that there will be, and eventually we get to a better estimate or a more accurate estimate of these parameters. But I kind of prefer to move on and deal with the uncertainties with the modeling, like with these hypotheses, in order to get relevant information. So I don't know examples for Quebec, but I would say pay attention to the upstream leakage, yes, but especially pay attention to the type of application, because that's going to be even more important. And that's where I've seen that a lot of the studies kind of fail. They don't devote the resources to be a little more accurate in this estimate.
Okay, thanks. The next question is, what market drivers were put in place? We're talking about regulatory, private industry, state federal government that drove early adoption of natural gas into port drayage operations in LA, Long Beach. We're talking here about the carrot versus the stick approach.
Yeah. So the motivation in California, despite the fact that California gives a carbon credit to natural gas, the real motivation in California is criteria pollutants, and those are particularly bad in ports. So those have been some of the original areas that have implemented this kind of measurements and have suggested natural gas trucks as a ways of reducing PM and SOx and NOx. So it's been addressed for the most part also with electricity, but also with natural gas. And but the motivation is different. It's not a carbon reduction motivation. It's a criteria pollutant motivation.
Yeah, thank you. Next question. Has the UC Davis team looked at comparable data for methane leakage in Canada or Quebec?
Actually, I think so, but I'm not familiar with it. But it will be in our website.
Okay. I guess people can follow up with you if they ever have more specific questions.
Yeah, definitely. That's my email, right?
So next question is, HPDI engines are not available commercially. That is 100% of commercial are CNG engines. 100% of commercial CNG engines are SI. Why are they included in the study, your study, as they lead uninformed readers to think that adopters can actually buy one?
Because my study is about possibilities. I'm testing the sensitivities. I'm testing what needs to be encouraged. And I know the HPDI has challenges. I know it's more expensive. I know because it's a dual fuel, it has to incorporate a lot of the after treatment for diesel, which is not good. But if we were to see that increased efficiencies were something desirable, maybe there will be a push for those. So my interest is not so much, so of course I need to be grounded in reality, so that's why I try to give all the background information I have on what is the reality, but I'm interested in actions I can take to improve what we have right now. So I have to test possible scenarios, even if they're not actually a reality.
Okay, thank you. Next question. What is the approximate proportion of SI trucks versus HPDI trucks on the road at the moment?
Okay, there you go. 100% SI versus 0% HPDI.
Yeah, so that's a quick one. So next, I am also surprised by the small potential reduction of GHGs from LNG long-haul trucks with combined diesel engines. Given the capital costs of retrofitting a fleet to natural gas, have you done some cost effectiveness studies on the cost per GHG ton reduced?
Not me, but two things about that. First, not a lot of LNG out there because it's costlier. So originally we thought LNG was going to be the storage option for long-haul truck, but looks like the reality is even long-haul trucks are using CNG. So not a lot of LNG out there. And the other thing is that most of the cost comparison studies I've seen found LNG trucks had payback period under 3 years, but that was with the larger spread between natural gas and diesel prices that we see today. So even though, you can see studies and you can see a number, like in 3 years, the investment pays back, but you always need to pay attention to the price assumption in the analysis. I haven't seen anyone more recent, but with both diesel and natural gas prices low, I'm guessing it's not. There's not a big of an improvement.
So next question, how realistic is it to reduce methane leakage upstream and vehicle to a point where natural gas provides GHG reduction compared to diesel? Do we have an idea of the cost and the complexity of this?
Yeah, so I don't have an idea of the cost because I don't know what it would cost to vehicle manufacturers to do that, and I have no idea what the aggregate cost to the natural gas industry would be to reduce the leakage. My guess is it's different kinds of complexity because we're talking about controlling just the trucks versus the entire system in terms of leakage, so different parts of the supply chain. We're talking about natural gas producers, we're talking about transmission companies, we're talking about distribution companies, so a lot more group of players there, and kind of more complex, more kind of a group effort. But at the same time, I think both things are going to be driven by regulation, and we have a methane rule in the US that fortunately for us, the Trump administration has not managed to repeal. So there is an effort, there is less and less leakage upstream. And we also have truck emission standards, and the auto industry is, I think they've always done a really good job at, pushing or reducing emissions to what the regulations tells them to do. So I don't know, both are challenging and both are necessary, I would say.
Okay, thank you. Next question. Apologies if you discussed this previously, but do you have insights on how the results change between global warming potential of 20 versus 100 years?
Yay. So definitely, I don't have, I'm not showing any results, but so we're using the 100-year global potential of 30. So even if you stick to one time period, the multiplier for methane or for different gases has been changing. So we use the latest number, which is 30, for the 100-year global warming potential. Now, if you were to use the 20-year, that would be worse for natural gas. That would be even less favorable for natural gas. And that is because methane is a long-term climate pollutant. That means it is more potent than CO2, and but it also dissipates. So most of the warming, you will have it kind of immediately and for about maybe 30, 80 years. For CO2 though, the CO2 stays in the atmosphere for much longer. So by using the 100-year, which is what we're using here and what most studies do, including IPCC, we are kind of not looking at the original warming that methane is. So we're going to have increased warming, but we're looking at the long-term picture. So if we were to switch to looking at the short-term picture in the next 20 years, then yes, there's going to be more warming. So natural gas are even worse in the short term that we're showing.
Okay, the last question from the people participating is, has the methane, oh, there's another one, but we'll see. Has the methane leakage linked to the diesel value chain been analyzed?
Not sure I understand. Has
the methane leakage linked to the diesel value chain been analyzed?
Oh, right. Yeah. Actually, yes. I'm not going to say it's completely accurate or fair. The natural gas and oil are co-produced a lot of the time. So methane leakage, and people have different systems to allocate the methane leakage, which is happening in conjunction to the natural gas or oil. We're using an average, and Argonne National Lab has probably more documentation on how they allocate it that I don't have right now, the actual specs. But yes, theoretically, yes, there is methane leakage in the oil supply chain too.
Okay, just the last question says, considering that HPDI trucks are unavailable at the moment and that the feasibility of reducing methane leakage is unknown, is it fair to conclude that relying on natural gas to reduce greenhouse gas in the freight transportation is generally a bad idea?
I would say Yes, I mean, unless you do these things, unless you reduce significantly the leakage, both upstream and downstream, and even then you don't have the HPDI, yes, it's. I would not favor it in the case of trucks. I mean, there might be other applications that it might be a good thing. Like, for example, in the case of marine, which is the other big example. I think in the case of marine, it could significantly provide benefits for two reasons. When natural gas is used in the ships, my understanding is that it's using, and I'm not a mechanical engineer, so I don't know the right term, but kind of not an internal combustion engine, but kind of a turbine, like power plant kind of natural gas engine, which is much more efficient than the internal combustion engine that is used for the bunker fuel. So in that case, you're switching from a ship that's running on diesel, that's as efficient because it's diesel engine, but you're switching to a natural gas power plant kind of thing, and that's much more efficient. And the other reason is that the bunker fuel is a much more dirtier fuel than diesel. So, I mean, again, it depends on the application. I haven't looked into, I haven't estimated natural gas use in marine, but that's what I would guess. It's going to be important.
Okay. Well, thank you, Rosa. This has been actually a really great, informative webinar. I think it provides a lot of information. At least in the context of Quebec, this is going to be a good starting point for us to be able to start discussing about the options for natural gas in the transportation sector. I just want to remind everybody that this video, this presentation has been recorded, and we're actually going to make it available on our website later on, as well as the PowerPoint of Rosa. So we're also hoping perhaps to organize a second webinar where she can present to us the results of her work on renewable natural gas in the transportation sector. So with that, I thank everyone. If you have specific questions, please don't hesitate to send them directly to Rosa, and everyone have a great evening.
Thank you.
Thank you.